Hello. In this lecture, we're going to look at camera control. And so this is an important application area for AI in games, especially 3D games with some rather complicated situations that can arise in moving a camera, especially one that follows the player. So like a first-person perspective game is pretty easy to deal with because the game player is directly controlling the camera. Same with it with like virtual reality as well. That will be a first-person perspective. But when you introduce a character that where you can actually see the game object as the game player see the game object you're controlling, that means that there is a virtual camera that has to keep that object framed, and there's different ways to do that. And it can quickly get to the point where it's complicated enough where you have to consider various AI approaches to dealing with the challenges that you face. So first of all, let's consider what exactly is involved with a camera with a 3D game. So your camera that you're interfacing with, like when you're building a game, you generally will think of it as a point camera. So everything goes through a single focal point. You don't have a lens. And for the purposes of rendering, you have a view frustum. And so this frustum is defined by the projection that's being performed. Through a single point, you're projecting onto a plane, which is your 2D array of pixels. And then so that array coincides with like your display that your game player is playing on. So because of those constraints and that sort of rectangular buffer shape, that defines these boundaries that when you're projecting based on the field of view. So you have the focal distance for the camera, and so that's going to define a field of view. And so that we can, based on the field of view that we have, we can figure out where the edges of the output buffer sort of stretch out into space. And so those would be the sides of this frustum. So if you see here in this figure, we have in view the top and the right, but the left and the bottom are sort of hidden underneath. So those four sides, those coincide with the edges of the array. And then we've got two ends to that sort of pyramidal shape. So there's the far clipping plane and the near clipping plane. And so altogether, the four sides and then the near and far clipping plane, those are all used to trim down everything in the world. And so only rendering what falls within that view frustum, and anything that sort of straddles outside and inside, those actually get cut, trimmed. So like the triangles that make up those surfaces, they get cut down to be triangles that are exclusively within the view frustum. And then that data within the frustum is used for projection. And so only things that appear within this view frustum, so this truncated pyramid shape, those are the things that get rendered. So you can aim the camera, however you like, because you've got these 6 degrees of freedom relative to the space. So that's XYZ translational movement, and then pitch, yaw, roll. So the rotational degrees of freedom. And then there's a 7th degree of freedom as well. That's the field of view that you can control. and potentially you could even, it's not normally done, but you could even control field of view independently for up, down, the vertical direction and the horizontal direction. But normally you have a locked or fixed aspect ratio, and so the field of view will like only be defined for the vertical or the horizontal. Um, but because of these constraints, it can be a challenge to figure out, how exactly to aim the camera to see what you want to see, or what the player should be seeing. So this whole issue of camera control is just related to what to look at, and then based on what to look at, we're going to run into some problems, and probably the biggest problem is occlusion avoidance. But there's also some issues with the fact that we have so many degrees of freedom. There's lots of ways to look at the same thing. So we might want to impose certain constraints, such as like always maintain the same up direction. So we're not like spinning around randomly. So technically looking at the same object, but sometimes upside down or not. But then there's a separate issue from just the basic geometry of camera control, and that is cinematography. And so cinematography is the art of film photography, and there are certain heuristics that come into play. Some of this is because it does the best job at conveying information, like in a story. And some of it is convention and meets the expectations of your audience. So there's familiarity with certain ways or processes to show moving pictures, especially when storytelling is involved. And so your game players might feel like something's wrong if these heuristics or laws of cinematography are broken. And furthermore, there within cinematography, there's an art to the positioning and placement of shots. And so there are these expressive constraints that maybe we want to emphasize some aspect of the story, which would call for a certain type of framing, maybe a wide shot or an extreme close-up or a cut or panning the camera. So there's different things that you might want to do, and that sort of expressiveness we would like to be present in games, that 3D games where, say, there's an in-game cutscene. The designers of the game level or the acting, they have to make decisions, and they don't necessarily want to be in a situation where they have to like micromanage the camera. Now there's a bigger challenge that there are many sort of unpredictable things that can happen in a game. So for instance, a game that's very flexible in terms of like events that occur, cause and effect, you might have character interactions occur in unplanned locations. So like you might have the basic interaction built into the game, but it's not constrained to be at one specific spot. Some games do that, but some are more flexible than that. So in just a normal movie, the director has full control, or at least they can instruct the actors to stand in specific spots, and then the cameras can be set up in these very specific spots. But even so, there might, from take to take of a scene, actors might move slightly differently or stand in slightly different locations. And so the camera operator is, of course, tends to be a human control, and they're going to be able to make moment-to-moment decisions for aiming, focusing, and so on. But in a video game, we don't have that. So if we are hoping to have any sort of cinematic shots, then we have to rely on scripting, either restricting what can happen, or if we have freedom, then that's going to suggest like freedom of where these different cinematic events can occur within the game world. That would suggest that we would need some kind of AI solution to resolve that. So there are different camera types that are employed in different games, which we've discussed a little bit. But so, for instance, the first person view, where generally there's probably no automation needed, but there could be transitions from that first person view, maybe to cutscenes, for instance, that running within the game engine. But third person types of views tend to be the much more interesting, at least from an AI perspective. So there can be orthogonal sorts of views, like a side view or top down. And these are very straightforward and involve just a fixed angle generally and distance. So you're locking everything in place and maybe following the player-controlled game object. But otherwise, there's not a lot of decisions to make. Occasionally, there'll be issues like related to occlusion, but not nearly as big as some of the others. There's also isometric view. This is where you kind of have a mixture of the top and side down, so you can see more of the environment, but otherwise a sort of a fixed angle. You can have other sort of arbitrary fixed angle positions as well. Then there are some other styles that you see, such as security camera type positioning. So this is where there's a camera like in a room, and a character can enter the room, and it'll be shown from that particular perspective. And it may or may not involve some degree of pan, tilt, zoom. But quite commonly, I think these tend to be fixed. There's also probably some of the more challenging sort of implementation is when you have follow or chase camera. And so this is an automatic camera that will follow the player-controlled game object, such as a character walking through the environment. So there's many games that fit into this sort of approach. There's also orbit cameras. This is where the player controls the camera around whatever game object that they're controlling. So they maybe have a joystick that's dedicated to moving the camera, and it rotates around in an orbit-like way. So usually there are 2 degrees of freedom that are restricted in some way. So maybe you can rotate around the full 360 degrees, but you can only angle up and down just so much. And then there's no roll type control typically, just to keep from getting confused or sick from unnecessary movement. And then there are hybrid approaches, and I'd say these are probably the most common of the like third-party chase cameras sort of situations, like like modern platformer type games where you have a third-person view. So you might, if you don't touch the joystick that controls the camera, it will sort of naturally fall back towards an AI controlled chase camera, but then you can override with as soon as you touch the joystick. So that would be the hybrid style. So there are some simple third person camera views. So the side, top down, and isometric, they all tend to be pretty simple in terms of implementation. There's not a lot there. And it really depends on if the game designer chooses to place geometry that might occlude the player. And so occasionally there is at least like a test to see if the character or the game object is occluded from the perspective of the camera. And this is performed generally would be like with a raycast. And so if that's found to be the case, you might hide the geometry that's blocking, for instance. But in many cases, this is just ignored. This problem is ignored. And if there's any, anything that occasionally covers up the character, maybe it's just used in a very limited way. And the player just has to be aware that there's this, whatever they're controlling is underneath, like a catwalk or a bridge. So that is a pretty common approach. Now there might be some smoothing or dead zone for tracking the character. This can be sometimes you see sort of like the character stays locked in position in the middle of the screen, and then so the camera basically has to follow the player by keeping them fixed in the middle. But then if you run to the edge of the world, you stop translating the camera, but then the character continues to move. And so this does a good job of sort of conveying that the boundaries of the world have been reached. But again, this is very simple, and I wouldn't say this fits into any sort of need for artificial intelligence implementation. It's just a hard-coded or scripted way of dealing with this scenario. So you just are aware that the camera has, it's followed to as far as it can go while still keeping the part of the game world framed. And so, it just stops. So that's a pretty straightforward thing to implement. So next up, we've got trigger systems for fixed cameras. These are where you have the security camera style, so the pan, tilt, zoom. They don't necessarily have to do any sort of movement. They can just have these different fixed positions. Often they're selected kind of for an artistic or cinematic sort of presentation. A great example that maybe some of you are familiar with is Resident Evil. And there are several games from the early 90s as well that I think inspired Resident Evil. Like Alone in the Dark is an old classic that had this style. But in these cases, there's really nothing that in terms of smarts for the camera, any individual camera. However, there is some degree of intelligence in selecting the cameras. And so this is almost always done through embedding the smarts in the game world. And you can do this by placing trigger zones in the world. So as the game objects move around, like let's say the player is controlling a character and that character goes through a doorway, well, you can detect through some sort of hidden collision objects or trigger zones that the character has entered the doorway, and that triggers a new camera position to be enabled. And so you just have a cut that occurs. So you always have just the one camera, but it takes on a new position and orientation. Now you may also have the security camera style features, the pan, tilt, and zoom, that could be employed as well. Now, in terms of those trigger areas, you can also have, and not necessarily have it all built into the game world. You could additionally just use the frustum boundaries of the camera. So that frustum that we looked at before, the truncated pyramid, you could detect when the game object begins to cross one of the four sides. And when that occurs, you then trigger going to like the camera position that's to the left, let's say. So here is a little clip that I'm going to show you of Resident Evil here. Actually, let me just jump ahead some past the...
A dining room. I think you'd better take a look at this.
What is it?
Blood. Jill, see if you can find any other clues. I'll be examining this. Let's just hope it's not Chris's.
Jump a little more here.
What is it?
Look out! It's a monster!
All right, so you probably noticed that as the characters that the player is controlling walk towards the edge of the view, that would initiate a transition to the next camera position. You may have also seen that some of the camera positions involve that pan, tilt, zoom. So at least the panning and tilting was occurring. And also there was a number of in-game cutscenes. And so it works really nicely with the camera strategy that was being used. It just sort of seamlessly fits with the scripted cinematic cuts fit nicely with the ones that were triggered. So overall, that was a good approach for the camera work in the Resident Evil and in the other games in the series. Another approach that can be used is an orbit camera. And so this is one where you were primarily interested in giving the player control of the camera. And so we still want the camera to follow the game object, like let's say a character we want it to follow, but the player gets to pick the angle. And so the player's only probably got like 2 degrees of freedom. Again, so we're not going to have the rolling rotation, but we can rotate around the character and then up and down, perhaps with some limitations. This it means that we don't really need any AI for this in the pure form. We might need some sort of special logic to deal with occlusions that might occur, though, and so we'll see some examples. So in fact, you rarely see like a true orbit camera, at least in commercial games. This is something that you can maybe easily do in Unity, but there tends to be some extra stuff going on just for usability in commercial games. So I've got an example here. This is a Unity camera script for player orbit, and it'll give you a good demonstration. So I'm going to see if I can jump to this scene here. So you can see that in this case, this is being played in the editor, but the person that's demonstrating is swinging the mouse around. So this is a mouse-controlled orbit camera. They're using like the keyboard controls to move the character, but the angle can be changed. And so it looks like this one has got a fixed elevation angle, so you can only rotate around. But you could also have one where you could change that angle. But that's a popular approach, and it sort of avoids some of the challenges that you would otherwise face if you want to have a more like automated sort of camera. So I mentioned before there's these issues with occlusion, and it can be a big deal for any sort of 3D scene. So whether you've got the orbit or some other style, this is something that you have to deal with. So keep in mind that view frustum that we talked about before with the near and the far clipping plane as we go through this discussion. So the sort of classic approach to figuring out if a camera can see something is to cast a ray from the camera's position towards the object of interest and picking like just one point in the simplest case, but you might actually have multiple points of interest on the game object, say the head, the torso, maybe the legs. It's sort of a game developers or designers decision, as for whether it's worth the cost of those extra tests. But even if you do, like let's say one ray cast, you might miss something. And so like in this case, only casting a single ray through the middle, this looking at this game object, I'm not even sure what that is. So we'll just call it a little robotic dog because I can't actually tell what it is in this picture. But we've got, so you see on the left here that it looks like we're looking down the edge of a wall, but there's this like weird cutoff part. And so what you're seeing there, that's actually the near clipping plane. And it has sliced away part of the triangle mesh that makes up that wall. So you're actually seeing past a wall that you should not be able to see past. And so that is a problem. And you could potentially solve it with more raycasts. But what we really care about is the near clipping plane, not where the camera is. The camera's position is actually meaningless because the way that like a OpenGL style camera works is different than a real world pinhole camera. So in the real world, if you have a pinhole camera in the real world, you've got the little hole that is all the light beams are being focused through. That's actually in front of the projection surface. So like if you make one of those shoebox you punch a little hole in a shoebox, and then you put like a piece of paper on another end, and then so you can look at the eclipse without directly viewing it. You just see everything focused through that point, and then the light being filtered through paper, or rather looking down through a hole in the box. There's different versions of those, but in any case, that little hole is on. It's in front of the projection surface. But in a video game or a computer that's rendering graphics, there's nothing that says that you have to put the hole there. It's just a mathematical model. So that point, like the tip of the pyramid, is generally where the camera is. But we're actually projecting onto the near clipping plane, or that's where our image plane is. It's coincides with that near clipping plane, and so because of that, that it means that all you have to worry about is you just need your near clipping plane to be in front of anything that might occlude it that you don't want to show up, or you don't want to be sliced up through the view frustum culling and clipping and culling process. And so that means you really want to raycast from the corners of the frustum. So you want to be able to extrude the near clipping plane towards your target, and then you're gonna. So those are what you would be testing. So just working out the geometry of what we're asking simplifies the problem, and it'll make it easier for like any sort of AI support that we need in the future. So if you understand this, it'll allow you your AI will work better. Now there are often these additional extensions to your camera that can come into play. Let's say you have isometric or something similar to isometric, like in this case, we've got like this fixed angle view in this video that I'm going to show, but we're going to use a raycast to determine whether to change the rendering characteristics of certain parts of the world. So this requires actually building in the world in sort of a piecemeal fashion, so you can identify these chunks of wall and then be able to swap their render settings to then make things appear transparent or a translucent effect. And so that allows you to see the game object. So let's check this out. So you'll notice that whenever the camera's view of the character gets occluded, that the surfaces of these walls will go translucent, and so that allows the player to see what they're doing. And we don't have to do any like movement of the camera. We just make the world adapt. So that's a really straightforward approach, but it is effective. So next up, we've got the situation where we have a follow or a chase camera, so kind of different terminology used by different people. And so these come in sort of different flavors. So one is where you've got a fixed offset, and so your camera is basically is just following the player. And so that's very similar to what we've talked about so far, but there might be some little exceptional cases when we do run into problems. Like we will generally stay at the fixed distance, but if there's a very rapid turn, there might be some smoothing in those cases, and then maybe changing the angle of the offset if, say, the character is jumping or doing a certain type of maneuver. It'll change briefly. And then perhaps also a few examples of like actually moving the camera closer, but which kind of blurs the distinction between what's a fixed offset camera and what's a fully simulated camera. And so you probably will rarely see a fixed offset camera except in maybe some early 3D games, and even some that you would maybe say are mostly fixed offset do have examples of more advanced features, even though they kind of tend to appear fixed offset. And so an example is Tomb Raider, which I've got a little demonstration of here. So you will see some smoothing on, like when there's a snap turn, a very quick, doing a 180. So you'll see the camera sort of animate a little and smooth out, going a little slower than Lara turns. But let's check this out. So you can see the camera in most cases it has this very immediate, rigid sort of movement, staying right behind Laura, except when she jumps. But you do see a lot of like kind of popping, and snapping in the movements. And but then you'll notice like when the camera is occluded, so there actually is something going on, recognizing that the camera would go through walls, and it changes the angle in those cases. So this is not strictly fixed offset, but it being an early demonstration or implementation, it does tend towards that sort of approach. And it does also, as you saw there, it transitions to these sort of cinematic views occasionally. And so the next example is a simulated camera, and this is one where the concept here is that, well, actually, let me go back to the text here. So we're going to have the camera, it's going to work as an independent game object. And this has constraints on movement. So for instance, maybe the camera will try to only move with certain speeds, for instance, and might have certain like context specific constraints. And so again, it's kind of hard to show. Tomb Raider really kind of fits into this a bit. There's certainly a few examples of things I would call a simulated camera. But another example is Mario, which I think has a lot more of those examples, but also it tends to make mistakes, again, being one of these very early games to tackle usability with 3D. Actually, let me jump ahead through these cutscenes. Still in a cutscene, but yeah. And in fact, there's like a story element. The little forget what the camera operators, Loki, can't remember his name, but so you can see here we've got this camera. It is sort of following at a fixed distance at times, but it also can change to these much more sort of cinematic views. It'll sometimes just stop. Let's see if we can find. Yeah, so like the angle can change in these much more arbitrary ways compared to in Tomb Raider, where Tomb Raider, it tries very hard to always be like right behind Lara. The only way you can get the camera to change these more extreme sorts of angles is to get the camera pushed up, like kind of back up against a wall. But here you can see the camera swinging out wide to give you a vantage point of the rolling giant bombs, or I guess those are just stones, not bombs. But and in some cases, it picks bad camera angles as well. So it's one of the challenges here. And so I'd imagine most of this is scripted. It's probably based on where Mario is standing, like walking to certain trigger areas, and then that sends a hint to the camera to now change like the angle, how the view is presented. So in terms of implementing this sort of camera, you will probably have characteristics associated with the camera itself, like treat it like a game object of some sort. It might have a collider associated with it. It might have some physical properties. It could have steering behaviors like a acceleration and maximum velocity and turn rates and so on. And so any sort of movement of the camera in attempting to follow what it's looking at, it's going to be limited by that performance envelope. And so that's also this game object can be used for detecting collisions. So if it's attempting to maintain an offset distance from, let's say, the character that the player is controlling, it might start backing up, and then it just bumped into a wall. And so, of course, it's not going to go through a wall because it's got a collider. So collision detection forces it to stay within the wall. So that means that you're going to maybe break the desired distance from the character, and then so maybe that distance gets smaller and smaller, and then maybe it gets too close where it's in danger of the near clipping plane cutting through the character, and you don't want that. So perhaps the camera could slide to the left or right. And so you're starting to imagine, hopefully, that there are lots of possible solutions when these constraints are broken. So you could slide the camera to the left, you could slide it to the right, you could slide it up. And so there's not really a right answer. And this is where some of the more artificial intelligence type of solutions come into play. Now that you can also have other sorts of smarts, like if the camera is following the player around a corner. So you might recall our steering behaviors discussion about, well, you don't want to start turning too early because that causes problems. So you might actually want the camera to keep a history of positions that it's seen the player, and then so go to that last position, maybe even speed up to as soon as the player's going out of view, speed up very quickly so you can get around the corner, minimize any time that the character is out of view. You could possibly even leverage something like A-star planning, maybe tracking positions on a nav mesh could be beneficial for understanding movement around the space. And so certainly, like, leveraging the maybe existing features in the game that are really meant to support AI for other purposes can be useful for the camera movement as well. And certainly also like we saw in Resident Evil with the triggers for switching the security camera views, we can also have hints built into the levels. So the Mario example, almost certainly there were like some triggers for when Mario entered certain zones to change angles for the camera, like to show the rolling stones. So the Uncharted series is probably a good example for hybrid cameras. This is where you have both a follow camera or chase camera and orbit capabilities. And so if you move without touching the camera, it will tend to slowly rotate and follow behind the back of the character. But you're always able to move your joystick and sort of override. And so this is a little test where I was actually demonstrating some of the blending animation for the video games class, but this can also serve the purpose of showing the camera control. So here I'm not steering the view at the moment. I'm just only using the left joystick to control the movement of the character. So it's just acting like a typical follow sort of camera. It does have sort of an odd angle that's set at this point. I think eventually I'll run over somewhere else. All right, there you go. And so there's also some awareness in the game knows where the next place in the world is, like these trigger zones. And in fact, I saw a little point where I overrode where the camera was trying to swing with the joystick. There's a lot of orbit control, I think, that I'm doing right now, just intuitively. There was a cut, so it actually recognized that it needed to perform a cut rather than flying awkwardly around, maybe introducing some motion sickness. So that the going over and around where the handhold of the wall ledge, the developers chose to employ that cut, and it worked pretty well there, I think. So I think some of the camera turns here are not from me turning, but actually being caused by the camera getting too close to the wall and it's trying to quickly swing around to a vantage point where there won't be any danger of clipping. So next up, we can start thinking about adding this cinematography concept that I mentioned before. So we can leverage some of these basic techniques we've seen so far for like the camera movement, checking for things like occlusions, maybe taking advantage of pathfinding features like the nav mesh, or maybe even like little bits of A-star type search. And so with that, we can support like artistic shots that help for presenting the narrative of the game, the storytelling. And so we'll look at a few examples from some research in these areas for virtual cinematography. And sorry, my phone is acting up here. So we can look at some ways in which, so first of all, an understanding of cinematography that we can take into account, and then we'll try to come up with like an algorithm to implement them. So this first one, the virtual cinematographer, a paradigm for automatic real-time camera control and directing. And so here we've got this concept of a line of interest, and so this actually draws from cinematography, and it's like consideration of, say, two characters interacting, and so we'll get take a little closer look at this. So when you have actors, like just say in a regular movie that are interacting, it's important to get the framing right for the conversations, let's say, that are taking place. And so if you want a close-up to look good, then you want to pick an angle that one where you can see the faces of the characters, but also have them like the right distances apart. And then that can change the further back you are. So like if you're just showing headshots, you'll maybe want a certain distance and proportions in the on the screen. But then if you have a more zoomed out view, a further distance view, then you might want a different distance between them. Now in actual movies, one thing to consider is that for the purpose of the movie, like in a close-up, the characters might be very close together, for instance, in an unnatural position. It looks natural in the framing of the shot, but if they are, let's say, being shown full body shot, then they would actually need to be further apart. And now in a movie, when you're filming it, you can just combine different takes, some where they're standing really close for the close-ups and then further apart, or maybe just change the angle, have multiple cameras and change the angle to kind of picking an angle the right way can get better framing. So, but the director can move actors around and stitch things together in certain ways. Now, in a video game, there's two possibilities. One is that the entities, whatever the models and the animations and so on, you could just say, well, they have a fixed placement in the world, and that's all we have to work with. The camera, we have to move the camera around that, and we can't change the world. It's just the camera can change its position, but we can't change the world. But another possibility you could consider is the camera needs certain things, and maybe it's the same way a director can move things around and edit together. Maybe the camera could send hints to the world and move the actors around But of course, that could create some inconsistencies that the player might notice, especially as you transition from the cutscene part to back again um, to the player controlled part. So, like if you've moved character positions around, then you know that might create some sort of disturbance in terms of the player's understanding of the world. But it might be something that we would wish to employ, this actually adjusting object positions in addition to the camera in order to fully create these cinematic sort of experiences. So there's various heuristics. Like if you took a film class, you would probably learn some of these things. So we saw an example of that line of interest at the beginning. One of these rules is you define a line of interest, like maybe involving characters that are important characters that are interacting, let's say in a conversation. So you don't want the camera to cross that line, because what that does is it changes the orientation of the characters, and it can be confusing to see like character A on the left and character B on the right, and then you switch to be the opposite by swinging a camera all the way around. Same thing like if you watch sporting events, like if you're watching football or soccer, you don't during the same period of gameplay, you don't swap the cameras to the other side of the stadium because your audience gets confused about the direction of the action. Another heuristic is to avoid jump cuts, and so we'll see an example of exactly what these are. But it's basically if a scene looks very similar and you jump ahead in time or change perspective, it looks, because there's those similar visual features. It looks to the viewer as if there's like a rapid speed up rather than a cut. So if you're performing a cut, you need to substantially change the subject of the view. So maybe looking at different objects, that would be appropriate for a cut, is if you're looking at entirely different objects, not the same object from generally the same perspective, just like, only just small changes like the field of view or the distance. It's also good to like use establishing shots. And this is establish a scene before you move to the close-up. So this kind of gives the viewer something to anchor onto or spatial awareness, I guess, of the scene. That can be useful. Let the actor lead. So if there is some sort of cue that the actor can provide before changing, so maybe the character like looks over their shoulder, then that would be the opportunity to cut the camera over. And then another rule is break movement. So this is a scene illustrating motion should be broken into at least 2 shots. So typically each shot is cut so that the actor appears to move across half of the screen space. And so this is just one of those kind of expectations that the audience will have, and just be more aesthetically pleasing. So here's again this line of interest example. So we've got different camera placements that we could consider, and so the line of interest was drawn through our 2, let's say, characters. And so we don't want to put any cameras on the other side of the line. And so we have an apex, and this is basically from a certain point with I guess like a target field of view, where we can fit both of the characters. And then we've got internal and external views. So internal views can be used for showing single characters, like one of the 2, and then external views are where we can sort of so we've got to stay on the correct side of the line, but we can angle so that we can see both A and B or B and A, and then so we can switch between the shots, and usually this will be dictated by dialogue between the characters and other interactions. So if there's any sort of physical interactions, it might be important to say like use an external shot. um, or using going from an internal to an external, and sort of moving back and forth to sort of show the direction or flow of conversation. And then there's lots of like little subtle rules for how best to do that. Here's an example of jump cuts versus a regular cut. So with a jump cut, you can see in the sort of the top left images here, the woman with the pushing the child in the stroller. So if you jumped from her walking, where she's further back, and then suddenly jump to her much closer, then that's what a jump cut would be, and it feels like a fast forward if you experience it. Whereas if you want to use cuts in that sequence of her getting closer, you would need to change the framing substantially. So maybe show both her and the stroller completely, then just show the lady, framing like a portrait view, and then for the baby. So that would allow you to shorten the length of the presentation, and still tell the story of the woman getting closer, and then seeing the baby. That could all be shortened, but not feel like these awkward fast forward sort of moments. So in terms of the camera movement in like the conversation scenario, we can move along that line of interest. So you probably recall from the previous figure that we were looking at those different external views. So we could frame both A and B and A. But you'll notice that we always have character A is on the left and character B on the right. But whoever we're paying attention to, like to see their facial expressions or mouth movements with the dialogue. We can choose those different angles, and so sort of swinging back and forth along this line of interest. And so now that we've got some idea of these sorts of heuristics for cinematography, we can start to think about, well, how might we go about employing any of those or implementing any of those heuristics in real time during like a video game. And so we've got like our application, our game event loop that's running, and it needs to interact with the rendering system, which would be typical of a video game. But we're also for this system, for the virtual cinematographer, we're adding that as a component, the virtual cinematographer. And so it needs to be aware of game world state, and so events that occur, probably related to storytelling, maybe trigger areas in the map, but also geometric information like spatial relationships. And also the virtual cinematographer needs to be able to talk to the application and make queries, so asking for specific information that can be used. And so the cinematographer is going to be sending controls to the camera, like camera positioning, so the 7 degrees of freedom. There also can be acting hints. And so these acting hints are situations where I mentioned before, you might actually want to control object placement, breaking from what we'll call the reality of the simulation. So where the characters are intended to be, maybe we'll kind of fudge things a bit for cinematic purposes, moving them like slightly closer. So you want to be, kind of cautious in how you do that. So like, for instance, if you're doing a close-up view of two characters talking, maybe that's a safe time to move the two characters like closer or further from one another, or relative positioning just slightly. And then when you cut to a different view and maybe they go back to their true positions, that's perhaps something the player's not going to notice and will otherwise appreciate the aesthetics of the generated cinematography. So that's a high level of how this system works. The cinematographer is constantly monitoring what's going on. It has the events have to tell it enough to know what is suitable for framing the views or not. I believe in this system, it didn't go back and forth between live game control, but it might sort of fall back if this was part of a interactive game that occasionally had in-game cutscenes. You might have it sort of fall back to a more classic sort of chase camera or orbit camera control, and then when the cutscenes kick in, then it starts to interject its cinematography. But as for the actual camera control, it analyzes the world state, the events that are occurring, and then from that, it selects when certain state machines should be employed. So these are predefined state machines that have strategies, and again, like everything we've learned about state machines before, all the various contingencies and so on, necessary for executing a plan are in these state machines, and they deal with different scenarios, like two characters talking, for instance, and then it can select different configurations based on environment constraints. So, like where is it best to set the line of interest? So that maybe one side or the other is better given the circumstances. So if they're up close to a wall, you probably want to pick the side furthest from the wall, for instance, for setting up your inside and outside camera angles. And then here's some examples of these state machines. So how they move from cutscenes. So this sort of built into these state machines are the heuristics for like moving back and forth across the line of interest. And so these transitions are probably dictated by conversation events or maybe physical interactions of the actors. But generally, you'll have a limited selection of these moves that you can take. And so this is for the two talking. There's also a 3-talk version, so 3 characters interacting. And so here you can see it actually calls the 2-talk state machine separately, and then uses internal and external angle views. So they can get a bit more complicated, but moving back and forth between these states, and each one of these states is associated with like the camera positioning. So these are parsed to, and we're converting high-level situations into specific shots or camera control processes as you're parsing through the state machines, and it'll generate the sequence of shots. So lots of cuts and different angles for each camera angle that we're cutting to. And here are some examples. Unfortunately, it's not a video that plays back, but at least you can kind of get an idea of like a sequence of the character entering the environment to like engage in a conversation. So we see the motion's broken up into the 2 different phases of moving halfway for one angle and then half the other, and then we see the conversation play out in the framing based on who's talking. So that is a potential solution that could be leveraged, as opposed to like totally scripting the camera in the game. So another type of camera control is demonstrated in this other paper, a model for constraint-based camera planning. And so they propose that a general purpose camera constraint system should support the following guidelines with arbitrary viewing goals. So these can be like application-specific constraints, such as certain subjects should appear in the shots or an orientation needs to be maintained. Then there is environmental complexity, so the camera should be able to deal with a complex environment that could introduce occlusions or restrict movements of the camera. World non-interference, and so this is the desire to avoid or minimize modification of the world to resolve any sort of constraints. So we've seen that in the previous paper was actually a possibility that where we move game objects to accomplish the scenes we want, but in this particular paper, they recognize that that it might be necessary, but it should be used as like a last resort. And then the last point for this general purpose constraint system is that there should be some means for handling failures, and that would suggest graceful degradation when constraints cannot be satisfied. And so that that could mean different things. So like perhaps using the translucent walls, for instance, or if you have to break a constraint, maybe there's a best way to do it, for instance. So this leverages a constraint system. So there's various constraints that are applied to the camera, and these can vary over time. And so all these constraints, as applied, will produce a camera placement that satisfies this. And there could be multiple camera placements that satisfy. But given the fact that we may have failures to solve, we have priorities in place. And so that means that we can perhaps a lower priority constraint can fail first before other higher priority constraints fail. So we need some means of defining this ranking, like with a weighting system, for instance. And also might help us more quickly find a solution. So here's some of the constraint types. And these can be activated through the progression of the simulation that's running. So like look at point, object and field of view. And these could change. So for instance, you might have an objective for the player to achieve. And when you get close enough to it, maybe that becomes an object in the field of view in addition to the player object. So now you have two objects in field of view would be defined. Then there's object occlusion, minimize, and maybe you prioritize and deprioritize at different points of the game. Object view angle, object distance, object projection size. This would suggest how much of the screen it fills up, at least in an indirect sort of way. Projection absolute or projection relative. Object depth order. So this would maybe be if you have multiple objects targeted as being in field of view, you could specify what order is the priority. Camera position within a region, camera field of view. So all of these things could be set or some combination. And here's some examples of like different projection sizes through the constraints that could be set. So depending on the field of view selection, you can get these different types of shots. Now, there could be some other constraints on the camera as well. So, for instance, how fast the camera can change parameters could be imposed. And so this can be really useful for the simulator sickness or motion sickness sort of problems that we discussed earlier. and so we might, for instance, favor position changes over angle and field of view change, because the movement in the field of view, the angle movement in the field of view change might be more likely to be sickening, for instance. And then perhaps also things could be done to favor like a cut rather than the movement. So like similar with what we saw in the Uncharted with when Nate climbs over the edge. Now, in terms of measuring constraint satisfaction, we need a metric to perform this. And so this is kind of similar to like our case-based reasoning matching of cases. So we have a degree of satisfaction for each constraint, and it's computed over like a normalized scale. So that way that we can easily compare these. But then we're multiplying by these priorities. So individually, each of the constraints has the satisfaction that solve whatever the nature of the thing is that we're solving is, like a distance or angle, that sort of thing. And then we have the priority order, and then we can multiply that out and take the sum. And so this gives us our cumulative constraint satisfaction rating. And this allows us to analyze multiple candidate camera positions. And so if we do have multiple and they each have different scores, so we can pick the one that has the best satisfaction of the constraints. And even if we aren't able to actually solve our constraints, we can have some sort of graceful failure, because we can find, well, something that maybe the closest of the candidates can be selected. So perhaps it would say have the slightly wrong field of view or some occlusion, perhaps, but wouldn't be completely arbitrary or hopefully not completely awful. So in terms of how you go about finding these specific points, in the paper they use an exhaustive generate and test process. So in other words, it's a brute force approach. They just try lots of approaches, moving the camera to different discrete steps of all the different possible values of camera position, aim direction. So like move here, try turning a little bit, try a whole bunch of different flavors of it. So, again, it's brute force, kind of computationally challenging, I guess. And, lots of stuff that needs to be done. So I don't have a video from this paper. However, there's someone had posted a video I found where they're attempting to build a constraint-based camera system. And so we can take a look at it. So here, the green box here is like a player-controlled object, and then the constraint system is constantly evaluating. And so that was a brief example of 3 additional game objects that needed to be in the field of view. So you can see the field of view increase to hold them all. Here was a change to a new object, and the camera has that vehicle performance model. It's limited in how quickly it can move to the new location. Though in that case, I think probably a cut would have been acceptable. It's a little glitchy here. It needs some more refinement, but it does seem to have some promise, given that all of this is defined just by constraints and trying to prioritize different views. So you can see it'll allow occlusions to occur at different times. But it's making like a best effort to frame as the constraints are specified. So yeah, I think you get the idea. It would have been nice to see this with, say, like a cut scene or something in addition to the movement. But so other approaches that can be taken to solving this, so like basically they're doing some with the brute force. This is like a random sampling effectively. That maybe they could cut back some on their sampling. But this is a good candidate for exploitation versus exploration sorts of strategies. So maybe some there could be some benefits for how we're considering all of these different candidate poses and trying to find good ones. Another possibility would be to leverage particle filtering. So I will I'll share a link to a little video just giving an introductory presentation on what particle filtering is, but that could be a good approach as well for like considering lots of different candidate camera positions that might work, and then if you find one, be able to act on that, and then still be considering other possibilities that could evolve over time to then become better at solving the constraints. So note that for real-time solutions, constraints can be difficult to evaluate because each camera placement frame must be rendered in some fashion in order to score for the satisfaction metric. That's I think really the big challenge is as you're considering these different hypothetical positions, you can't necessarily score them without evaluating them, at least to some degree. And we've seen how just a single raycast is often not enough to figure out if something can be seen well or not, like based on occlusion. So it's and considering doing that for all of those different candidate positions could be very expensive. Maybe with graphics hardware, like the GPU with the parallelization that's possible, perhaps you could set up some relatively efficient way to analyze those different poses. So maybe even like rendering to an extremely low res view would be useful. Doing so off screen, it's not something that the player would see, but that would be leveraged for selection of the appropriate views, perhaps. All right, so that wraps up our look at AI as applied to camera control. So again, we've got the basic aspects of the camera automation, dealing especially with the problems of occlusion, which is a big challenge. But then further applying the sort of the camera movement and so on, applying that to cinematography. And so that's an even bigger problem and probably more directly an AI sort of challenge. All right, yeah, so we'll stop there, and like usual, if you have any questions about today's lecture, feel free to reach out.